Hello. So today we're going to be talking about Newton's law of gravitation, which is quite interesting. So first off, let's define Newton's law of gravitation. What is it? It basically says that is the force between two objects is directly proportional to the product of their masses. So let's say the mass of object one and the mass of object two, and it's inversely proportional to the distance between these two objects squared. So we're going to write it like this. If we want to have an equation that we can use, we're going to be using this equation. We know what these two are, but this is going to be a new thing, and this is basically G, which is our gravitational constant. And this gravitational constant is equal to 6.67 times 10 to the power of negative 11. And this can be found in your formula booklet, so you don't have to worry too much about memorizing it, but still good to know or to have in your head so you don't have to keep flipping. But we're going to see this G quite often. So it's our gravitational constant. We should know that. And this is the equation that we can use to define the forces between two objects. When we're talking about two objects in space, when we're talking about on a large scale, we use this same equation. And so it can have quite interesting applications. So before we move on, let's talk about force fields. And this is going to be very similar to electric and magnetic fields because we like to keep things the same throughout them when we're describing fields, especially because we want to have the same type of rules so we can define them very clearly. So let's say we're on Earth right now. Ooh. Maybe we're jumping, I don't know. And we have a little tree here. This is basically us on Earth. The way that our field looks on Earth is uniform. We have a uniform field here, where basically our field lines are parallel and equally spaced between each other. Another way, or another type of field that we have is a radial field. And so now let's think about the Earth kind of on a larger scale, interacting with other planetary objects. The way that this would actually look is something like this, where basically we have a radial field over here. It's not uniform, our lines aren't quite parallel, but they are all pointing towards the Earth's center. And so we can see that the difference that these field lines have is their spacing, and their spacing is actually corresponding to the gravitational field strength at that point. So when we're over here, because these lines are evenly spaced, we're basically going to have pretty much the same gravitational field strength, which is actually why we have our gravitational acceleration as 9.81 meters per second. And it's constant, usually we say, no matter where that object is falling. However, when we're talking about on a much bigger scale, it's slightly different. Over here, when we're closer to the Earth, we can actually see that our gravitational field strength is stronger than, let's say, if we were over here where our lines are further apart. So let's start talking about this gravitational field strength and how we can define it. Oh, spelled that wrong. So the gravitational field strength is the force per unit mass at a point in a gravitational field. We have G is our force per unit mass over here. And so obviously we could define that with our units like this. Another way that we can say this is G is equal to our gravitational constant times m, which is the mass of the object, r squared. And so one of the things that I want to make clear are that these are two different kinds of m's. Over here, if we were thinking of a person on Earth, or let's say the moon, m is going to be the object or the mass of the object that is being affected by the bigger object's gravitational field, or whichever object's gravitational field actually. And m is going to be the object whose gravitational field is affecting the other mass under consideration over here. So it's good to be able to distinguish between these two things. And we're going to have to keep that in mind when we're talking about this. So let's talk about orbital motion. We're going to go on a much bigger scale here. We're talking about, planetary objects orbiting each other. So to talk about orbital motion, we can use Kepler's law. But first of all, we have the tools to be able to derive this. We know that our force here is equal to this. I've written this slightly differently, but note that m is equal to our first mass, and m, or small m, is equal to our second mass. We know this from over here. And if you can recall from 6.1, another way for our force, or to describe circular motion, is this. So when we combine these two equations together, we can derive Kepler's law. So I'm going to go ahead and do that right now. It's quite methodical, actually. Let's first start off by equating the two. We can cancel out two of our masses right now. And so if you can recall from simple harmonic motion, our omega is also written like this, 2 pi over t whole squared. And we can substitute this in. Oh, sorry, not whole squared, but actually when we substitute it in, it is going to be squared. And then this is basically going to give us Kepler's law. And this is Kepler's third law specifically. And this basically tells us that t squared, or our time period squared, is proportional to the distance cubed. It gives us a good proportionality law, and we can use this equation when we want to talk about objects in gravitational that are affected gravitationally and are moving in orbit of another object, which is going to link perfectly with Newton's gravitational law.